Large applications that are deployed at client location or those which are deployed in the embedded devices may crash or show up functional errors randomly. It is a common practice to record execution snapshot of such applications into dedicated log files, and then these log files are passed over to developers for debugging. As developers, we will be required to analyze these logs and trace bugs. Upon successful fix, appropriate patches or a new binary image is sent over to client. Or in case of an embedded software, a new firmware is made available for download. Logs can contain code dump of program when the crash happened, or some backtrace of the program which led to a problematic code. While debugging such apps, a developer needs to carefully walk through logs, interpret the log description, and then locate the bugs. We may not always have access to debugger or a debug-ready binary build. In such cases, we may need to proceed with bug hunting completely based on log info provided. We will spend a couple of sessions learning this raw approach to bug hunting. These sessions will equip us with bug hunting techniques that can be applied when we are required to carry out debugging without any sort of debug assist tools or debug libraries. Let's begin with a sample log. This is the defect log of an application that crashed in a production environment. We'll first look at this log data, analyze it to start our bug hunting process. Look at this first line here. It reports that the program has received a signal 11. Signal level 11 simply indicates a segmentation violation. It means the program has crashed because of some invalid memory access. The next line here shows up the exact address where the fault occurred. It means when program was trying to access this particular region, the crash occurred. And then further down you can see the instruction pointer's address when the crash occurred. It means this was the instruction, the code segment. When this instruction was in execution, the fault occurred. And further down we have the error code, the architecture-specific error code that shows up the reasons why this particular invalid access occurred. And then we have the PID of the process when the crash occurred, followed by a dump of the registers. These are all the register values recorded when the crash occurred. And then you have the recently accessed stack data, the complete dump of the recently accessed stack, and then further down the call trace. The call trace is of the recently called functions, the whole backtrace of the program when the crash occurred. And then further down in the last, we have the instruction that caused the error, the code instruction that caused the error. It's been shown in the binary. Usually we don't require this particular code instruction to start our debug process. The information in the first 3 lines is quite enough to begin our debug analysis. Let's begin our debug process with this information. Line 4 of this log shows up the error code, the page fault error code. Now x86 architecture that defines the error code description for page fault like this. Error code is a byte field of which 5 bits are valid. If bit 0 is set, it means it's a protection fault. If bit 1 is set, it means the access was a write access. If bit 2 is set, it means the memory region being accessed is user space. And if it is not set, the memory region being accessed is kernel space. Bit 3 is reserved and bit 4 is used, or it is set to indicate a fault occurring because of an instruction fetch. Now if you look at the log's error code 007, this error code when converted to binary bit form looks like this. It means the first 3 bits are set. It means the fault occurred because of a write access on a space or a region of address which is user mode. So the first bit is set indicating production fault, second bit is set indicating write access, and third bit is set indicating the access was on user mode address space. Let's use GDB and then find out why the fault occurred. We'll take both the approaches. First, we'll take a look at how to use GDB kind of tool to track down this kind of issues, and then we'll use manual approach without using any sort of tool to track down the bug. Let's begin our GDB session. MyString. So it started now. As per the log here, the instruction that caused the fault. This is the instruction that caused the fault. What we'll do, we'll begin with looking at the source line of this instruction. So we'll use the command list. We'll try and print that particular source line of the address that caused the instruction. So if you see this dump here, it shows up the source line as line number 24. And line number 24 happens to be in a function called MyStringReverse. And in this particular function, the line 24 is initializing the value of the pointer referred by string to this particular location temp. It means we are copying the value in str pointer to a location pointed by a pointer temp. So obviously this particular line is causing the fault. And if you further look at the instruction log dump, or if you look at the other log dump, the fault has caused by accessing this address. So it obviously means the temp was pointing to this particular location. And this location may not be writable. And that could be the reason why the fault occurred. But let's try and probe into why that location is not writable. To further dig into details, let's try and understand what this str is and where it's coming from. If you observe the line number 22 here, the temp is being assigned the address of str plus length. It means whatever string is being pointed by the str pointer, that particular string length is being calculated, and the end address of that string is being stored into temp. So the end address is now this particular address referred by our log. Now this address could be in the read-only segment. There are two reasons for that. There are two possibilities of that. One, str could be pointing to a region of memory which is not writable. Second, the length that is mentioned here may be exceeding that particular string location or string size. You can see here in line number 21, we are calling a function MyStringLength. We have passed the str pointer, which is holding a string, and then this particular function is returning the length. So if the length was calculated in the wrong way, there is a possibility that str plus length could lead this temp to a memory region outside the string area, which could not be writable. But before we suspect all this, we'll try and look into where this str is coming from. Now here, if you look at the call trace provided in our log, the fault occurred in this particular function. Probably this is the base pointer of the function MyStringReverse because the fault occurred here. And then the caller function stack is this. Let's try and see that caller function stack in detail. Let's say list star. We'll try and take this address, the caller address. So you can see this is the main function stack. It means main function was invoking this particular routine MyStringReverse. And you can see line number 39, that particular function call. Now this particular function call MyStringReverse from the main function is being invoked by passing the argument name. Name, let's try and list all, let's say line number 30 to 44. You can see here the main function has got a pointer name assigned to a constant string, and then that particular name is being passed as an argument to MyStringReverse routine. So this particular routine is referring to a string of length 14 bytes. It means this particular address that is being shown up in the log should be the address of the string with 14 bytes added. Let's try and look at where the address falls into. Let's use info files. Since we are not running the application in GDB session, we could not use procmap files. So we look at info files. Info files here shows up some details. You can see here, info files shows up a detail that RO data is in this particular region. It means read-only constants and strings are in this particular region. And if you consider this log address, which is the base address of string plus 14 added to it, then if you subtract the 14 bytes address, you would end up at somewhere 0x64, 0x8048D64. That's where you end up. So obviously this means that particular address is falling into this region. And because it's falling into this region, any access to write to it, like we are doing in the case of that instruction temp, that fault instruction that we have seen earlier. So we are trying to update that particular region, and the temp is pointing to an address region which is read-only, and that's causing the fault. This is a very simple example where it's very easy to track down the fault. But what we'll do now, we'll try and look at the same using manual procedures without using a tool like a GDB. Let's make an assumption we don't have the executable built with debug information into it. In such cases, we cannot use GDB because GDB relies on that particular debug symbols to show up the source instructions. We need to now search around for alternate methods to debug such applications. We look at one alternate method that relies on binary disassembly tools like object dump. We'll begin with this particular tool or this particular command called objdump using a -d, which is a disassemble flag. We'll try and disassemble the executable dump. MyStringReverse will redirect that into a file. Let's choose a file something like this. Let's call it as dump. So now the file got created with the name dump. You can see the file now will consist of the execution dump or that particular binary dump of the file. So now let's look at the log information. The log information shows up some details. Watch this. The previous GDB session will terminate this. So you can see here the log shows up the instruction which caused the fault. Let's take this particular instruction offset and search the location of this in our dump file. So this is the dump file. We'll search for the address. You can see here this particular address falls into an instruction that's in the function MyStringReverse. It means the problem is in MyStringReverse function, and that is the instruction causing the issue. Since now we know the instruction that caused the problem and the function in which the instruction was, we can start our analysis by analyzing the stack trace of this particular function. So we'll try and do a step-by-step analysis of the stack trace until we reach this particular instruction that caused the fault. We know that a function begins with preamble. Preamble's objective is to set the EBP and ESP to a same address in the stack segment during the beginning of the function. EBP remains in the same address and ESP is decremented by the amount of stack data, amount of local data of that function. On function return, again ESP and EBP return back to same address. So these two instructions here are the preamble instructions of this particular function called MyStringReverse. Before we start looking at the stack trace, let's make an assumption that EBP contains a value X and ESP contains a value Y. Assuming that EBP is X and ESP is Y, after the first instruction is executed, the stack would look something like this. You would have ESP pointing to Y-4 because it is decremented by 4 bytes to push the value of that particular register EBP. Assuming that EBP contains the value X, you'll have X value stored. Obviously, this particular X should be the EBP of the caller function. So the caller function is main function in this case, so this should be some value of the base pointer of the main function. Now this particular Y-4 remains to be the address of the EBP for this particular function. Because the next instruction of our preamble copies the value of ESP into EBP. Currently ESP is referring to Y-4. So EBP should also be copied with Y-4, which happens to be the base pointer for the stack frame of this particular function MyStringReverse. This particular base pointer is valid throughout the stack frame, because as local data of this particular function gets allocated, ESP is moved down and EBP will remain the same location. During function return, this particular X, which is the main function's EBP, is brought back assigned to the EBP register. So as long as MyStringReverse function is running, y-4 should be the EBP. We can now actually resolve the actual address of that particular base pointer, because we have the error log for the application. Watch this. The error log of the application provides us a dump of the registers and the values of the registers which were recorded when the application crashed. We know that the application has crashed in the function MyStringReverse. So if you look here, the EBP of that particular MyStringReverse function is being shown here. It is a hexadecimal number. For ease of understanding, let's go with 57508, which means this is the location of the base pointer of that particular stack frame. Let's apply this. Watch this. So now, y-4 obviously should be that particular location 57508, and then whatever ESP was pointing to, that is y should be plus 4 bytes of this. So obviously it should be 5750C. So now the ESP is at 57508, EBP is at 57508, and the value of y was 5750C. We are yet to resolve this particular X. Let's move further now to the next instruction of our function. The next instruction of our function is about allocating local data for the stack. You can see the instruction in the binary code here. We are trying to subtract 0x14 from ESP. It means we're trying to allocate 20 bytes of stack data. So as a result of that particular sub-instruction, you should see ESP moving further down by 20 bytes. ESP would be set with 574F4, and EBP would remain at 57508. And here you have 20 bytes of local data allocated for the stack frame of this function MyStringReverse. The next instruction in our source is a function called to MyStringLength. Notice this, here we are passing the MyStringLength with the address of that particular string constant. This function needs to find the length of that particular string pointed by this pointer str and return the length. And this particular str is an argument received by this function MyStringReverse. So whatever the argument we have received from the caller function, we are passing that particular argument address to this particular function called MyStringLength. The assembly equivalent of this would be like this. We are moving 0x8 EBP into EAX accumulator. Obviously we know this, the first argument begins at the 8th offset. So the first argument, this happens to be the first argument and the only argument for the function. To access this we need to move by 8 bytes. So we are moving 8 bytes higher memory to above the EBP and then accessing that particular start address of str and copying that into EAX. The next instruction, before we go into the next instruction, this particular EAX now should hold the address of that particular string. Since we are not aware of the address of the string, let's make an assumption that the address is Z. The next instruction is to copy the address of EAX into a location pointed by the stack pointer. So this particular binary instruction is moving the EAX value, which is the address of the string, into ESP. So this particular top of the stack will now be stored with that particular address which we have assumed as Z. Now the function STRLength is invoked. This particular function needs to find the length of that particular string pointed by str and return that particular string value. The return value of the string is being stored in the -8 of EBP, which happens to be the location A. So in this particular location, we are holding the return value of the function MyStringLength, and this is the address of that location as per the stack dump that we have looked earlier. Now we are reaching the next instruction in our source, which happens to be str plus length. whatever length has been returned by the MyStringLength function, we are trying to set the temp pointer to that particular address. So the base address is stored in str, we are adding length to it to move to the last address, and we are storing that particular address into temp. The assembly equivalent of this, the binary equivalent instructions of this would look something like this. The first step is to move the -8, which is the length variable, into EAX. The next instruction is add this particular 8 of EBP, which is the argument. str is supposed to be the argument with EAX, and then move the result back into -4 of EBP. -4 of EBP is the address of temp. By the end of this operation, the stack would look something like this. The temp, which is -4 of EBP, would contain the address Z plus A. Z is the start address and A is the length. The next block of instructions in our source code is a while loop construct. Using this loop construct, we are trying to copy that string in the reversed order into the address pointed by temp. This particular loop construct begins with a condition check that verifies if that particular string pointed by str is a valid value. For this particular condition, we are executing these 3 different machine instructions. The first instruction moves the address of that particular str to EAX accumulator. In the second instruction, we are trying to access the first offset, the first byte of that particular location pointed by str, and the value of that first byte is being moved into EAX. In the third instruction, we are verifying if that byte value is a valid value and is not 0. If the value is not 0, the condition is set to be true, and then we jump into loop body. If the value is 0, the condition is set to be false, and then we jump out of that particular loop body. It means this particular loop code will involve appropriate jump instructions along with these 3 instructions mentioned here. If you look at the complete dump of this particular function with the addresses that we acquired from our log of the object dump, you could see here these 3 instructions that we were referring to. Those 3 instructions are in these 3 addresses: 8048715, 8048718, and 8048711B. Now the previous instruction that we have executed was setting up that particular temp to the address of that particular string, to the end address of string, and that instruction was this particular address, 80486SD. So here, since the loop should begin with jump, we have a jump instruction which is unconditional jump to 8048715, which means after this instruction we jump to this particular location where the loop is evaluated. These 3 instructions are evaluating the loop condition. In our case, from the error log, we can verify that the error log has shown the instruction address where the fault occurred as 804870B. So obviously that particular error log was referring to this particular instruction 804870P. And this block of code would be executed only if the condition check evaluated to true. It means the condition check was evaluated to true, and then this instruction has pushed the application back, because jump or not equal, this has pushed the application back into the address 804871D, which happens to be an address located here. This particular code is the loop body code, and while executing this particular loop body, the fault occurred. Let's try and take a look at the loop body source instruction. The loop body source instruction is to move that particular string stored in the string pointer into temp, and this again has 4 instructions at the binary level. The first instruction is about moving that particular string into EAX accumulator. The second instruction is about copying the first byte of that particular string pointed by EAX into EDX. The third instruction, we are trying to access that particular local variable or local pointer address temp and moving that into EAX. And the fourth instruction, we are trying to copy the data from the EDX into EAX. And if you look at the addresses for these instructions, you would find the addresses in the binary dump. This is the line. 804870B is where actually we are moving the value from that particular pointer str back into that location temp, and that is where the fault occurred. If you look at the log shows up that that's where the fault occurred. It means with our stack analysis we have reached a point where the instruction fault occurred. So we now precisely know that the instruction fault occurred while executing this particular instruction in our source. While executing this particular instruction in our source. Now let's try and take a look at the current state of stack. The current state of stack is this. The current state of stack is we know the ESP location, we know the length is stored in the stack, the temp is pointing to the end of the string, and that particular location's address is stored in temp pointer. So we have assumed z plus a to be the address of temp, we have assumed the length of str to be a, and then we have assumed that x is the value stored in the EBP of the main. Let's now back into our crash log file. Actually, we have the entire dump of the stack values that were present when the fault occurred. So this is the state of the stack and the values in the stack when the fault at this particular instruction occurred. Let's try and use these values and resolve these a, z, and so on. Because now precisely we know what values were in stack. So the top of stack was 8048D7E, which we have resolved earlier, and that is the same. It means str was pointing to this. The second value is 0, and you could see the second 4-byte offset was filled with zeros. And then further down, 4 more bytes were filled with zeros. And then you can see a value E here, which was the location, or which was the value in the location length. It means length was pointing to a value E. And length has been returned from the particular function called MyStringLength. MyStringLength was computing the length of string and then returning that particular value. Now E in hexadecimal will be equal to 14 bytes in decimal. It means the particular string was of length 14 bytes. So that particular string was str pointing towards Veda solutions, and that string length is 14 bytes, and 14 is the correct value. It means my STRLength computed the correct length of the string. The next instruction is about temp. The next part of the stack is about temp. Now the temp is pointing to the end of that particular str. Since we know the base address of str and we also now know the length of it, we can actually compute the address of temp. But let's go by the stack dump. If you look at the stack dump here, it shows up 8048D7E. It means temp was holding the address 8048D7E. And then the next value here was 57538, BFT 57538. It means the EBP of the caller function was this particular value, BFT 57538. This is where the stack frame of our function ends. All the other values that we see here, these values are the values of the previous stack frame, which happens to be the main function stack frame. So the main function stack frame, the top value was 8048761, and then 804870. If you look at this 8048761, that should be obviously the return address of the main function. And then the main function had a string, which is a local data for main function, so it was pointing to 8048D70. Like this, you can track down the main function also to find out where the address of str has come from. Now the point is we are not able to write to that particular location pointed by temp. Let's try and find what's wrong with that particular address. We'll make use of again the object dump tool to find out where or which region of the address space the temp is pointing to. That should give us a clear indication of why the fault occurred. Let's switch over to the terminal mode and watch the object dump. So if you look at the object dump, let's say use the pipe operation more. You could see here now, let's get back to presentation once. The address that we are looking for is 0x8048D7E, and if you watch here, that particular address falls into this section called read-only data. So temp is referring to RO data section, and that's the reason why this particular application crashes when it tries to write down some new data into that particular region. So we have debugged the program. We have used almost all the information available in the defect log. We have used the instruction pointer value to find out the line of code that caused the fault. We have used the error code provided in the log to know which space the error occurred, the user or kernel mode. We have used the register values to know the ESP and EBP dumps, and we have used stack data to find out corresponding values of variables at the time of execution when the crash occurred.